I want to move on to a new topic for this class. It's one that you have seen before because you've all taken linear algebra. So I just want to go over a few of the basic things before moving on to why it is important for us. So we have this idea for a basis for a vector space, and I just want to rehash some of the language that we're going to be using repeatedly. So a basis is a collection of vectors. So we say the collection v1 through vn. And at this stage, I'm going to drop the arrow notation over the letters to indicate vectors. I'm going to be writing too many vectors for that to be a really effective way to write them down. So I'm just going to drop that notation, and we're just going to write them as letters. All right, so we say that this collection v1 through vn is a basis. If the following things are true. So the first thing is that this collection has to span the entire space, and I'll remind you what that means in just a second. So the span of v1 through vn is the entire space. And the second thing, not only do they span everything, but they're all essential vectors in a sense. And what by essential I mean that this collection v1 through vn is what we call linearly independent. All right, so let's go over what these two notions mean. First, the notion of a span, and second, the notion of linear independence. All right, so the idea of a span, the span of a set of vectors is just defined to be all sets of linear combinations of them. So I'll remind you what that means. All right, so the span of v1 through vn is defined to be the set of all linear combinations of the v's. So that would be, c1 v1 plus through cn vn. And here the only stipulation is that the ci's are scalar. All right, so we've got just a set of all linear combinations, and again, this idea here is what we call a linear combination. Of the v's. All right, it just means that you take a bunch of scalars, rescale your vectors, and add them together. This is what we call a linear combination. All right, so the span of this set of vectors is just defined to be the set of all linear combinations. You want to think of this as all the other vectors that you can build just from the vectors that are in your collection. And we'll do an example of this in a little bit. The idea of linear independence. So the idea here, right, so linear independence loosely means that none of the v's, right, so the vi's, is a linear combination of the others. This is loosely what it means. So we can write out what this means in an exact sense. All right, so linear independence means that none of them is a linear combination of the others. So if one of them were a linear combination of the others, let's see what would happen. right? So let's say if, for instance, right, this is just a hypothetical. If, for instance, V1 were a linear combination of the others, well, what this would mean is that V1 could be written as a linear combination of all of the others. Right? In other words, we'd be able to find C2, C3, C4, up through Cn that would make this statement that I just wrote down true. And checking to see if these numbers exist, there's a procedure to do this, of course. So the main thing that I want to stress here is how you actually check for linear independence. All right, so what we have here is this would be linear dependence, right? This hypothetical that I introduced here, right? If V1 were a linear combination of the others, this is basically saying that the collection that we started with is a linearly dependent collection because one of them, namely V1, could be written in terms of the others. So how do you check for linear independence, right? This is what I want to get at here. Well, if I were to subtract V1 from both sides, then this linear dependence condition could be rewritten to say that 0 would be equal to, in this case, minus V1 plus C2V2 all the way up through CnVn. Right? And the important part about this is that we're able to find one of these coefficients here, at least one of these coefficients, which is not 0. That lets us add them all up with rescalings of each other, right? So a giant linear combination of these vectors with not necessarily all 0 coefficients, that adds up to 0 on the other side. All right, so this is what it means to be linearly dependent. You can find non-zero numbers, which are these c's, the coefficients in this sum. You can find non-zero c's that let you add up all the vectors and get 0 as an outcome. So this gives us at least a convenient way to write down the definition of linear independence. All right, so we say the collection V1 through Vn is linearly independent if C1V1 plus all the way up through CnVn equals 0. Well, if this tells you, right, if this implies that all of the c's are equal to each other, and moreover, they're all 0. All right, so if you look at a sum, a giant linear combination of all of the vectors in your collection, which is V1 through Vn. So you look at this linear combination, which is this statement right here. That's a giant linear combination of all of your vectors. And if you set that equal to 0, and go ahead and solve for the c's to see what you would get, if it turns out that they all must themselves be zeros, which is what this says, then you would say that this collection is linearly independent. All right, so this is the idea. Boiling it down to actually what we set up here, right? So starting with this definition and sort of working backwards to what we have up here, what you're really saying is that if all of these c's have to be 0 in order for this linear combination to add up to 0, what you're saying is that you wouldn't be able to isolate one of them, say V1 for instance, to be a linear combination of the others. All right, so these two conditions are saying the same thing. This definition down here right, at the bottom here, which is the definition of linear independence that we're going to work with. This is really saying, if you do a little bit of work to understand, to sort of peel back the layers, this is really just saying that none of the v's can be written as a linear combination of the others. Right? And so they're all independent in a sense. And what this means for us is that they all contain different information from each other. All right, we'll see what that means in just a second here by way of an example. All right, so what I want to do now is just quickly go over an example of, say we're in R2, right, so we're just in the usual plane, and let's say we have this collection B, which is comprised of the vectors 1, 0, and 0, 1. All right, what I want to do is go ahead and show that B is a basis. So the first thing we need to do, you don't have to do these in this order, of course, but the first thing we have to do is check that the span of B is the entirety of R2. Right? In other words, if we start with any vector in R2, let's say it's called V, and it has coordinates, maybe, I don't know, A, and that's a terrible A, A and B, right? So given any vector V, which has coordinates A and B, we need to find the coordinates, or the coefficients, C1 and C2, which make C1 times 1, 0, the first vector in our collection, plus C2 times 0, 1, the second vector in our collection, equal to this vector that we started with, AB. Alright, so this is the idea. And again, I'm just using the fact that, if I go back a page here, right, the definition of the span is right here. It's the set of all linear combinations of the vectors in your collection. And the definition of a basis here is that the span of your collection of vectors has to be the entire space. So what I'm doing here is I'm starting with an arbitrary vector which lives in our space. So an arbitrary vector in R2. And what I'm doing is I'm checking to see if I can find these coefficients C1 and C2 that makes this linear combination add up to the vector, this sort of randomly chosen arbitrary vector in R2. All right, so this is the idea. And this is not hard to work out at all. Multiplying these scalars in and adding the vectors together gives you, on the left-hand side, C1, C2, and the right-hand side, AB. And this tells you exactly what C1 and C2 have to be. Of course, they have to be the coordinates, the x and y coordinates of the vector in question. All right, so C1 equal to A, C2 equal to B works. In other words, it makes C1 times the first vector plus C2 times the second vector add up to this arbitrary vector in R2. Right, so these values work, and if you want a punchline, thus the span of B is the entirety of R2. Okay, so the next thing we have to do is to check that the two vectors that comprise B are actually linearly independent from one another. And this amounts, if I go back a page, this amounts to checking this criterion down here, right? That if a linear combination of the vectors in our collection adds up to 0, then all those coefficients must actually be 0. So what we need to do is check linear independence. And what we're going to do is suppose that C1 times 1, 0 plus C2 times 0, 1 is equal to the 0 vector. And what we want to do now is figure out what values of C1 and C2 would make this work. Right, so doing the exact same thing we just did, this would tell us that C1, C2 must be 0, 0. In other words, C1 must be equal to C2, which must be 0. Right, and this tells us that because all the coefficients did have to be 0, right, there's no other way to make this work other than to have them both be 0. This tells us that that B, the collection we started with, is a linearly independent collection. And because we have a collection that is linearly independent and spans the entire space, this tells us that B must actually be a basis. And B has a very special name. This particular basis, which has the vectors 1, 0 and 0, 1 in it, this is called the standard basis for R2. It's a standard basis. And these vectors are often denoted by E sub 1 and E sub 2. And they're called the standard unit basis vectors of R2. Right, so these are, this is really just checking, they're called the standard unit basis vectors because they are, in fact, basis vectors. Alright, so let's do one more, a little bit more complicated example. Actually, before we do that, I do want to point out here, I have a little bit of room to draw a picture. If we look at a picture of R2, right, so here's your, your typical XY plane. Then the two basis vectors that we just considered are 0, 1, which is right there, and 1, 0. I'm sorry, I got those backwards. 1, 0 and 0, 1. That's these two vectors here in light blue. And just sort of eyeballing this, you can clearly see that these have to be linearly independent vectors. And that's because there's only two of them, right? So if they were linearly dependent, that would mean that they would have to be, since there's only two of them, that would mean that one of them has to be a rescaling of the other. And they're actually orthogonal, so there's no way that they're a rescaling of one another. So you can just sort of visually see that this has to be a basis for R2. Also, one small point that I want to make here is that because B has two vectors and it's a basis for R2, we say the dimension of R2 is the number of vectors in any basis for it, which is 2. Alright, so we have this idea of dimension at play too. Alright, so if we move to this example, let's take another collection of vectors. I'm really just going to make some up here. Let's do maybe 2, 1 and 1, 2. Alright, so let's say we have this set of vectors. The question, is S a basis for R2? So I'm going to have you, in just a second, I'm going to have you pause this and work this out on your own. Work out the details, I mean. but I can go ahead and spoil the punchline for you. The answer is yes, it is. And again, you can get an intuition for this by looking at the picture. And this, again, the picture works because we're only in 2 dimensions. So it's not hard to draw the picture. It's not hard to visualize these things. Our 2 vectors are 2, 1 and 1, 2. So 2, 1, we're going to come out 2 on the x-axis and up 1 on the y. So that's going to look something like this. And 1, 2 is the other one. Right, so we go over 1 and up 2. So something like that. And you can see that they're not just a rescaling of one another. And again, we know from the last problem that the dimension of R2 is 2, right, which isn't really surprising. The dimension of R2 is 2. And what we have here is S, which contains 2 vectors. And those vectors are linearly independent, which you can see from the picture, but I'm going to have you prove it just by checking the calculation here in a second. So 2 vectors which are linearly independent. And this tells us actually that because the numbers match up, you've got the dimension of the space is 2, and you have 2 vectors which are linearly independent, this actually implies that S is a basis. You don't need to check anything else beyond this, except the formal proof that, or the formal checking, whatever you want to call it, that that this collection actually is linearly independent. So I want you to take a minute here, pause this, and go ahead and check linear independence for S. So let me know if you have any questions about that last example, if you're running any problems with it. So the next thing I want to do is move up a dimension, right? So this is going to be a situation where it's not going to be as easy to visualize what's going on. And so we're going to have to rely more on the algebra. And this is, typically how these things go. This is why it's called linear algebra. You really have to rely on the algebra more than the visualization. So we've got this collection of 3 vectors. Is this collection a basis for R3 is the question. So, it doesn't really matter where you start. You could check the span first. You could check linear independence first. It doesn't really matter. Maybe let's check linear independence, which is what I was calling point 2 before. All right, so check linear independence of S. And the reason why I say it doesn't really matter which one you check is because, number one, there's the correct number of vectors in this collection for it to at least be a candidate for a basis. Right? There's 3 vectors. There's 3 vectors here. And we know just from experience that the dimension of R3 is 3. All right, so there's at least the right number of vectors. So it doesn't necessarily matter which one you check first. And in so checking both of them, right, in checking linear independence and the span being the entire space, you're actually going to be doing the exact same calculation twice. It's really basically a carbon copy of the same work that you would just be doing twice. All right, so it doesn't really matter which one you do. So let's check linear independence first. All right, so again, what we're going to do is suppose that C1 times 1, 1, 0 plus C2 times negative 1, 0, 1 plus C3 times negative 1, 1, 2. Suppose this all adds up to the 0 vector, 0, 0, 0. All right, what we want to ask now is what can we say about the values of C1, C2, and C3? All right, so again, multiplying, distributing the C's into their vectors and adding them together leads us to the following. In the first component, we're going to have C1 minus C2 minus C3. On the right-hand side, we still have the 0 vector. That hasn't changed. In the second component, we're going to have C1 plus 0 C2 plus C3. And in the third component, we're going to have C2 plus 2 C3. Okay, so this gives us a system of 3 equations in 3 unknowns. All right, so just rewriting this as a system. That would be C1 minus C2 minus C3 should be 0. C1 plus C3 should be 0. And C2 plus 2C3 should be 0. And now, there's a variety of ways that you can go about this. All these different algebraic ways that you can work on solving this thing. One thing I do want to point out is that there is a very direct relationship between this system that we're trying to solve and a very specific matrix. Okay, so if you remember how to figure out how to rewrite systems of equations into matrix equations, the thing that you're looking for are the coefficients on all of your variables in here. And so I've added them in green here. And so what this equation or system of equations is really saying is that if we take the matrix 1, -1, -1, 1, 0, 1, 0, 1, 2, and if we multiply that by the column vector C1, C2, C3, this should give us the output vector 0, 0, 0. Alright, so there is a very direct way of translating these things to and from matrix equations. And if you notice, the columns of our matrix are exactly the 3 vectors in our basis. Right, that's what these 3 column vectors are. Okay, so the long and short of this is that you have to solve this this system, and there of course is a variety of algebraic ways that you can do this. If you translate it to a matrix equation, you've got all of linear algebra at your disposal. If you don't want to, then you've got basically algebra 2 from high school at your disposal. And so what you're just going to do is start manipulating these equations, solving for one variable in terms of another, and plugging stuff in, right? However you want to imagine this. So maybe I'll take the second equation, and if I solve for, let's say, C1 is equal to negative C3, then I can plug that in up here, right? That might do something for me. So C1 minus C2, just recopying that first equation, minus C3 is equal to 0. And if C1 is equal to negative C3, then I've got negative C3 minus C2 minus C3 is equal to 0. In other words, C2 would be equal to negative 2 C3. And if you notice, that's exactly what this equation tells me as well. And that is typically bad news for being able to solve this system of equations, because this means that 2 of the equations in this system of 3 equations are redundant. They actually tell you the exact same information. And so what this really means is that we're not going to be able to solve explicitly for all 3 of these variables and get exact values for them. We're going to have infinitely many solutions. All right, so since this is actually the same as equation 3 here, we are going to have infinitely many solutions. And that is bad news in terms of us figuring out exact values for C1, C2, and C3. We're not going to get them to all be zeros. right? There's going to be infinitely many of them that work. And that means that this collection is not going to be linearly independent, therefore not a basis.